Math 2312, Chapter 1, Functions, Section 1, Functions and Function Notation, Video 10, Basic Graphs. We're going to conclude this section series of videos by reminding you of some basic graphs of basic functions. Later we'll learn how to take these basic graphs and transform them into graphs of more, not more complicated functions, but functions that have more moves to them, based on these basic functions graphs. I have 8 of them that I'm going to show you, and I'm not going to develop any of these graphs. Push comes to shove, you can make a table for all of these, connect the dots, and go, oh yeah, that's what the graph looks like. But as we progress through this course, these are 8 graphs that you should just know by looking at their functions and going, I know your graph because you're a basic function. The first function we're going to look at is f of x equals a constant. By a constant, I mean any number. So in this case, I have f of x equals 3, but it could be any number like 2 or -4 or pi or 19/3 or -7.3 or any other constant. A constant function produces the same output for every input. So vary not to 1-to-1, meaning that no matter what your input is, the output is always the same. This function says, I don't care what your input is, your output is always 3. Remembering that when you do a function, the input is the x coordinate and the output is the y coordinate. A function like f of x equals 3 says, you can give me all the ordered pairs whose input is whatever you want, or whose first coordinate is whatever you want, but whose second coordinate is 3. If we were to find 3 on the y-axis, then every point on the horizontal line that passes through 3 on the y-axis would be a point on that function's graph. In other words, f of x equals a constant is a horizontal line, and that constant is its y-intercept. The graph of f of x equals x, well, first off, this function is actually called the identity function. I like to say it's because it preserves the identity of its input. Give me a number and I'll give it right back to you. But there's a more algebraic reason why it's called the identity function, but we won't go into that right now because we would have to talk about function composition, which we haven't done yet. But regardless, this function says whatever your input is, I'll give it back to you and that will be your output. So for example, if I put in 2, I get out 2. If I put in 3, I get out 3. And if you find all the points whose x and y's are the same, you get this perfect diagonal line. When I say perfect diagonal line, I mean it bisects quadrants 1 and 3. If you want to think in terms of angles, this makes a 45-degree angle. When we talk about trigonometry later, that'll be kind of important. F of x equals x squared, we've already discussed. It's a parabola whose vertex is at the origin and opens upwards. You can locate some specific points to find its exact position. For example, the point 1, 1 is on it, so is the origin, so is the point -1, 1. In fact, you'll notice that the origin and 1, 1 are going to be on a lot of these graphs. X cubed, it looks like a parabola, but the biggest difference is when you take a negative number and square it, it becomes positive, which is why the left half of the parabola goes up. But if you take a negative number and cube it, it stays negative, which means for negative x's, the y values are also negative, so it goes down. So it kind of looks like a parabola, but it's technically a little bit steeper, but the left end points down instead of up. It does go through the same 2 points, 0, 0, and 1, 1. Again, those are going to be some very common points to these graphs. Again, the left end points down because when you cube a negative number, it stays negative, as opposed to when you square a negative number, it becomes positive. The fourth graph is the square root of x. Now here's where we have to be careful. This function actually has some domain issues, which we'll get into more detail in the next section in this chapter. Namely, we don't want to square any negative numbers because it'll create imaginary numbers, which don't have a place to live on this graph. So the smallest value we can put in here is 0. The graph of f of x equals the square root of x looks like the top half of a parabola opening to the left. The other half is not part of the graph. A function by itself, a square root by itself comes out positive. This doesn't have a plus minus on it. If it did, it wouldn't be a function in the first place. So this function can't possibly be all of the parabola. It would violate the vertical line test, but it is the top half of a sideways parabola opening to the right. By the way, if you wanted it to be the negative, the bottom half, you would have to put a negative in front of the square root. Cube root kind of looks like square root with one major difference. Oh, by the way, 0, 0, and 1, 1 are still points on these graphs. It's amazing, they just show up all the time. The cube root of x is kind of like the square root of x, except it's a little bit flatter. It's really hard to see unless you see them on top of each other. But that's not the main difference. That's a subtle difference that it's hard to see if you don't draw perfectly. And even if you do, it's hard to see. The difference between cube root and square root is you can cube root negative numbers. Why? Because when you cube a negative number, it comes out negative, so I can uncube it and get into the cube root of it. So you get part of the graph down here. In fact, it's the same shape as x cubed, it's just oriented differently. Those are inverse functions without getting into detail, and there's a relationship between their graphs, but the main thing I want you to know is that the graph of cube root of x does have a negative portion down in quadrant 3, whereas the graph of the square root of x just stops or starts, depending upon your perspective, at the origin. I'm assuming everybody knows what absolute value does to a number. If it's positive, it leaves it alone. If it's negative, it makes it positive. There's a more rigorous definition of absolute value, but let's work on the assumption that you know what it does to numbers. If I put in a positive number, it doesn't change it, which means for positive numbers, it's just this. However, for negative numbers, it does change it. It changes it to the opposite. For example, if I put in negative 1, it gives me 1. If I put in negative 2, it gives me 2. And if I put in negative 3, it gives me 3. So it gives me a diagonal line going that bisects quadrant 2. It's almost like, it's not almost, it is this graph with its negative portion reflected to the top, because that's what absolute values do to negatives. They reflect them up here and make them positive. Absolute value is a V. Value starts with V. You're welcome for the gimmick. And of course, this absolute value graph does go through the points 0, 0, and 1, 1. Very common order pairs, even back here on f of x equals x. Oh, by the way, there's another couple of ordered pairs that show up, but not all the time. Negative 1, 1 shows up. It shows up there. It shows up here. Negative 1, which is down here, shows up on the cube graph and shows up on the cube root graph. So there are some more common points besides the origin and 1, 1. This guy, don't worry about him. F of x equals 1 over x is an interesting graph because you can't draw it in one continuous move. You have to pick up your writing utensil. Think about this fraction for a second. First off, it's never equal to 0, because for a fraction to equal 0, you have to have 0 on the top. And we never have 0 on the top. So we can't get 0 out. But not only can we not get 0 out, we can't put 0 in because it would cause the denominator to be 0, making the fraction undefined. Because we can't put 0 in, I'm going to draw a vertical line right down the middle on the y-axis. Because we can't get 0 out, I'm going to draw a horizontal line through y equals 0, in other words, the x-axis. There's one branch in quadrant 1 that starts really high close to the y-axis, plummets down, goes through the point, you guessed it, 1, 1, and then as it keeps going, it gets closer and closer to the x-axis without touching it. And then you have the exact same phenomenon down here in quadrant 3. It does go through the point -1, -1. But as you go further to the right, it gets closer to the x-axis, and as you go further to the left, it gets closer to the x-axis, and as you get closer to the y-axis, it starts plummeting downwards. These two dotted lines in reference to this function are called asymptotes, A-S-Y-M-P-T-O-T-E-S. Singular is asymptote, but an asymptote is a line that a graph gets closer to without crossing it. And again, the reason this has asymptotes is because number 1, we can't put 0 into the function, and number 2, we can't get 0 out of the function. We can only put in numbers close to 0 and get out numbers close to 0. For example, if I put in a million, I'll get 1/1,000,000th, which is really close to 0, but not 0. And I can put in numbers close to 0, like 0.001. If I put in 0.001, the output would be 1,000. So I'll put in a number really close to 0, and its output is really high. But I just can't put in 0, and I can't get out 0. So as we move through this course, these are some graphs that you just need to know by looking at their functions. Constant function, which is a horizontal line, the identity function, which is a perfect diagonal line, the squaring function, which is a parabola, the cubing function, and this graph is actually called a cubic, the square root function, which is the top half of a parabola opening to the right, the cube root function, which is a sideways cubic, the absolute value function, is a v, and this is called the reciprocal function because it takes the reciprocal of a fraction, and it has two asymptotes and two branches, each of which approach the two asymptotes. I'm going to walk around over here and turn off the video. Oh, by the way, this is the last video for this section.